Good afternoon. My name is Alex Casella. I'm one of the co-authors of the paper for which this talk is based on. So the name of the paper is Performant Large Language Model Agentic Framework for Conversational AI. It is a little confusing, like it's a mouthful to say that, but really what the paper is about is a new framework, a new way of querying language models so that they are more efficient, more performant, for conversational AI, voice AI use cases. So like a little bit of background about myself. I'm the co-founder and head of engineering at a voice AI company called Thoughtly. Before this, I have worked on a number of different startups, and then before that, I was a tech lead at IBM Watson. The co-author is Wayne. He is a machine learning engineer at Thoughtly, and formerly he was at UC Berkeley doing ML research. So we learned about the need to implement this sort of like a framework and just generally finding ways to optimize querying language models and using language models at Thoughtly. Thoughtly handles millions of calls for thousands of global customers. We are the voice AI company that replaces human call centers and human call staff for enterprises and for different types of businesses across different domains. Our customers are in legal, they're in healthcare, they're doing sales, they're doing inbound customer support. They have customers of their own, so Thoughtly is B2B2C, and Thoughtly's callers, so the callers which are the customers of these companies that we service, they come from a range of different demographics. So some of the callers are a bit older that may prefer to speak a bit slower. Some of the callers are from low-income areas, and we generally support different use cases, many different use cases. What we have learned is we have to be able to handle very dynamic yet very linear conversation workflows. So what that means is, so what does dynamic mean? Dynamic is when you're having a conversation, the conversation can go anywhere, right? So that's typically the case when you're doing outbound, especially when you're doing like lead activation, lead conversion, sales type of use cases. Customer support, on the other hand, customer support use cases are more linear because they generally follow the flow of the intended conversation path. So we have to be able to handle edge cases very gracefully. And edge cases can include a bunch of different things. There are a lot of variables at play. Something like background audio can be an edge case. Something like callers saying they want something else completely different from what you had expected could be a different edge case. In addition to that, we have to be able to fetch any relevant information, to the caller's latest input and apply that to the conversation. So this typically comes in the form of caller asking questions about the businesses that they're calling. So that could be business hours, hours of operation, whatever. Do you service over the weekends? That type of things. In addition to that, we have to execute different tasks before the call, during the call, and after the call, right? So these kind of like automations that involve maybe updating some CRM, or integrating with some booking system, some calendar booking system. And we have to be able to support all of that in the form of nodes and edges, right? So our customers come to us and they build these like workflows. I know the last talk said workflow is not a good term to use, but we call them workflows. They come in the form of nodes and edges. And then the whole point here I'm trying to make is there are a lot of different variables and a lot of different edge cases that we have to cover, which means very large context windows sent to the language model that induces a lot of hallucination. Here is an example of a extremely simple workflow. So in this workflow, this is like a healthcare use case, right? So in the top node, in node 1, the instruction for our agent to say, our agent is the agent that talks and replaces the human agent, the human staff. So the agent says, thank you for calling X Healthcare. Can you give me a bit more information to route your call? And then the two different outcomes that we're anticipating here is first, caller can confirm their willingness to continue and ask for additional information, or the caller wants to hang up the call. In which case you would go to each of the subsequent nodes and then go from there. So that's generally the idea of how you go from node to node. Here is another example of a slightly more complicated workflow, and this is to illustrate that the number of nodes and edges can grow quite significantly. When you're calling the language model with all of the context about these nodes, obviously when you're in the beginning of the conversation, the context window is a little bit shorter, but as you go towards the end of the conversation, right, as you get to node 20 or 25, your context window really gets huge because it also contains the instructions to all of the previous, nodes, right? So how do you kind of solve this performance problem and reduce hallucination? Before I answer that, by the way, the answer is really what this paper is kind of based on. Before I answer that, I want to make sure everyone is on the same page about how each conversation turn is handled. So in voice AI, there is a orchestration stack that everybody follows. So this involves a caller sending their audio payload to a carrier, and the carrier then sends that payload to the voice IP provider. So the voice IP provider would be a Twilio or like a Vonage or Telnex or someone like that. They then send the audio payload to us, to Thoughtly. Thoughtly then transcribes the speech and turn it into text. The text that is then sent to language models to identify where you are in this workflow. And then once we figure out where we are in the workflow, then we generate the appropriate conversation based on what the caller just said, including information that is relevant, the RAG information, right, that you retrieved, including any actions that you have to take at this conversation turn, so on and so forth. So once we get the generated conversation from the language model, then we send that to a speech-to-text service to turn that back into audio, and then that gets sent back to the voice IP provider. The voice IP provider then sends that back to the carrier, which then gets sent to the caller. So all of that is a synchronous loop and takes a long time. Where everybody in this space is constantly trying to improve the latency and cut the latency as much as possible. But one of the challenges, of course, is that this loop is relatively synchronous. But yeah, so what did we learn from all of this? To summarize everything I've said so far, natural conversation is dynamic and linear, depending on the use case. Outbound calls tend to be more conversationally dynamic. Outbound calls have more edge cases. It is very, very difficult to account for all of the edge cases. I've personally audited thousands of calls, if not more, and I'm hearing all sorts of random things that come up in the calls. So also callers love to ask questions during the calls, especially when you're trying to sell them something. And in-call actions have to be triggered at the right time. This is very important. The order of things matter. Like, for example, when you're booking an appointment, you want to get the appointment availability before you call the booking action, right? And your agent has to be smart enough to understand that you're doing that when you're supposed to be doing these things. The challenge is if we're in one of these graphs, right? If the action of querying the booking times is in node 2, but then the action of actually booking is in node 6, you don't want your agent to somehow navigate to node 6 before it gets to node 2, right? Of course, you can circumvent that with different clever techniques, such as like global nodes and whatever, but that's a challenge that's a different topic that we can talk about at happy hour. But yeah, so the next point is it's very important to control how much information is fetched, right? So when and here I'm specifically referring to the top K value if you're using something like just like a vector database, or if you're using something a little bit more fancy like Letta, then it's still very relevant of how much information you're actually fetching and then feeding to the model. Language models hallucinate very often. There are a number of benchmarks done based on tests, right? I think you've all seen those numbers. So the numbers are very good. They're in the 80%, 88%, whatever, 87% in terms of accuracy for instruction following. That is not really the case. I don't know how some of those numbers came about. I think probably a lot of battles were done in those battlegrounds, and they just picked the highest number out of probably 30, 40 turns. But anyways, language models hallucinate more than you like them to. So you definitely want to be able to do everything you can to get around that problem. And relying entirely on language models is very risky, which is kind of what this paper and this presentation is about, is how to work around that. And a lot of this becomes a systems problem because what we're doing here is balancing accuracy, which is the alignment with sort of this the best step finding, right? Understanding where you are in these workflows, and the alignment with kind of like the ideal conversation response when you get to that step. So that is a accuracy problem. And then the other problem that we're balancing is latency, is how to solve this very, very quickly. Okay, I guess I just talked about this. I forgot I had this slide. So generally in this industry, sub 1,000 milliseconds, so 1 second latency for each conversation turn is expected. A year ago, that was very difficult to achieve, but now with the advancement of all of these different text-to-speech, speech-to-text providers, and language models, and just all the techniques that people have been applying, this is no longer the case. 1,000 millisecond latency is very much achievable. People expect the agents to be indistinguishable from humans. And if caller ever goes off track because of any of the edge cases, you want to very gently steer them back, very gracefully doing so, because you want to appear natural and human-like. And you also want, at the same time, want to progress towards the business goals ASAP, because every single one of these calls have a goal in mind, right? That you're not just talking to humans to talk to humans because you like the sound of their voice. You want to achieve something. You want to resolve a customer complaint, or open a ticket, or transfer them to a human, or convert a sale, right? Or something like that. And on top of all of that, you want to be able to do this in dozens of different languages. So if you get this wrong, then callers can block your call, which is, business lost, so we don't want that. During each conversation turn, there are two things that generally happen. The first one is step finding, which is where we are in the conversation flow. The second one is conversation generation, like I said, which is what we do once we get to, what we say once we get to the step. Generally, these steps occur naturally and separately. When I'm having a conversation with a human, you may not realize this, but in your mind, you're basically doing step finding and conversation generation. So when I'm talking to, I don't know, like Amazon support, if I have a complaint about one of my orders, what the humans on the other end of the line is doing is basically this, right? They're thinking about following some instruction workflow and saying, okay, Alex complained about this item, and he ordered a size large, but he said it's smaller, so therefore I should recommend like a medium, but first a medium size. But first I have to check to see if there's inventory availability, so something like that. So one of the optimizations that we did is handling step finding and conversation generation concurrently at the same time for more linear workflows. So this is more practical for more linear workflows, and I'll get into why. So previously, before any of this optimization is done, what we do is send everything that I said to the language model, and then rely entirely on the language model to figure out what to generate and figure out where we are. I'll give a second to take a picture of this. But the problem with that is obviously too much hallucination. So there are a few different versions that we propose in this paper. The most basic version is, instead of passing information of all of the nodes and edges, we use the last identified step as the contextual anchor. And what you want to do is use some sort of like step finding algorithm, or just record your visited path, and then go from the start node with the very first node to the contextual anchor, and then pass all the information of every node to the context window. Whereas remember previously, what we're doing is we're passing information of all of the nodes and edges, right? Even the ones that are further down the tree. So okay, so I want to make sure everybody understands this, because this is like rather important. So previously what we did is, for each conversation turn, we'll pass information of all of the nodes here. But now, like what we propose in the basic version is, if you're on node 2, you would only pass information about node 1 and node 2, right, to the context window, because the other steps are pretty much like locked. And we also pass information about node 3, because node 3 is an immediate child of one of the ancestor nodes for which you're currently on, which represents a jump that you could have done, right, in the conversation. So, so here in node 5, if you're on node 5, then you will do 1, 2, 3, 5, 4, and 6. So that's the first thing that we did. Figure out where I am. Okay, so we figure out the path, and then we take a subset of the nodes and edges, and then pass them to the context window. So that's the basic version. The optimized version is we generate a response, right? We do the conversation generation as we usually do. But then instead of using language models completely to identify the next step, we use vector scores, which is just math. It's just a mathematical calculation to figure out the semantic similarity. And the vector scores, we check the vector score of the similarity between the generated conversation and the instruction of the next step, right? So if they're similar enough past a certain threshold that we care about, then we can like fairly confidently say, this is the step, this is the new next step, that's where we're on. And you don't have to spend 500 milliseconds or 800 milliseconds or whatever to then call a language model and do the same thing. But of course, you want to be very careful about your sensitivity about that threshold number so that you don't make a mistake here. And of course, what we do is we use language model as a backup if we don't hit that confidence threshold to be safe. So what this means really is a combination of math plus language model to achieve this balance between linear and dynamic conversations. So we have a few hypotheses, and we did some experiments. The first hypothesis is basic version achieves a higher average similarity than the baseline. The baseline is a naive approach where we pass everything and use language model for everything. Basic version is the version where we pass a subset after doing pathfinding. Right, and then the optimized version is that plus the vector scoring. So there are some pretty straightforward, intuitive hypotheses where the optimized version does better than the basic version does better than the naive version. So how do we set this up? We had a few different hypothetical workflows, each one with about 50 nodes. And these nodes are very simple, right? They just have instructions that say, please wait a moment while I process your refund. We have different scenarios that we're running through. We have 5 different types of scenarios. For example, refunds, scheduling appointments, general questions about a business, and so on. And then we had a caller agent and a staff agent. You can think of this as like a normal conversation agent and like an NT agent. So they're just talking to each other, simulating the normal conversation. And we wait until each turn is done, and then we initiate the next turn, right? So in this test, I have to have a disclaimer saying that we don't care about interruptions. Interruptions is something that's very real in actual conversations, but for the sake of this experiment, we did not do that. So the staff agent would basically read the entire business workflow and do the same thing that we always do, and then they talk to each other turn by turn. For each turn, we have what is a expected golden response. Golden response says, okay, on this turn, if we got to this step, then you should have generated this, right? This seems very simple, but the language model does not always generate the right response. So we have a golden response to evaluate against on every single conversation turn, and we basically generated a bunch of different data sets and then compared the semantic similarity between the golden response and the actual final response. And we did that manually, just to be safe. So that's kind of what I described. Sorry, I made these slides like a long time ago. So I kind of forgot like if I'm skipping some slides. But that's kind of what I said, which is we figure out the cosine similarity to the golden response for every single conversation turn, and then for every single conversation, we aggregate all of the results and average them for each turn, and then we average all of the aggregated results for all of the conversations, and then compare them. So the results are like this. By the way, you can find the GitHub repo for which we did this. It's open source, and then you can run the experiments yourself. But yeah, so the link is in the paper. But yeah, so we achieved we basically got what we wanted, right, for the hypotheses. which is the frequency of conversations that are more aligned occurs more often in the optimized versions. These are some numbers just to break down the graph that you saw earlier. So what does this kind of mean? And I think this means, well, even though Thoughtly does voice AI, what we did here is applicable to not just voice AI, but just generally agentic AI, where you have to go through some workflow to optimize, because you have to use language models. And this is, in my opinion, it's a good first step, but it's not it's not where we want it to be yet, because even with this approach, if you have customers that expect the accuracy of upwards of like 90%, this is not going to meet it. But this is certainly an improvement over existing ways of doing things. It is important to reassess often, because in this space, new things are happening all the time. So it's very important to kind of like figure out if some service may have come up to help you with this problem. But yeah, that's the presentation. Does anybody have any questions? Thank you.
Hey, have you ever tried the speech models, like speech to speech? I mean, how can they reduce all this entire stuff?
Yeah, so we experimented with like a lot of the large language models, and then we experimented with real-time API from OpenAI and those kind of things. We haven't experimented with, for example, 11 Labs conversational AI. But what we saw is right now it's still better to do this ourselves instead of relying on a single vendor that orchestrates the stack themselves. The accuracy and the alignment is just not there for them. And the ability to react to interruptions and the dynamism of the voices, they're just not comparable at this point. But they may be in the future.
Speech model itself, not like an API or something like Novasonic or any GPT-4.
I mean, that's kind of what real-time API does. Okay. Is it would orchestrate that for you. It would take audio data as input, and then, well, it's very easy to configure in a way to be able to do that.
Hey, can you please tell us a little bit more about the specific metrics you use to evaluate the success of the system in general, like maybe user frustration or anything like that?
Yeah, totally. For production use, we have more ways to evaluate if something is an improvement. For this experiment, we, like I said, didn't evaluate interruptions, did not evaluate emotions or anything like that. Or like things like the amount of silence or gap in between the conversation, or latency, really. But in production, there are all of those things that you want to measure. A lot of it is qualitative at this point, but I suspect that at some point someone will come out with some benchmarks that are quite comprehensive, and then we'll use them. Maybe we'll make them, those benchmarks. But yeah, you're absolutely right. There are many things that we need to measure against in real life.
Thank you. It was a very interesting talk, and thank you so much for showing us the examples of workflows. And I would like to ask you, how do you experiment with defining the workflows and the nodes of that? And if you also experimented with using agents in order to optimize that?
Yeah, for sure. So I would say book a sales call with Thoughtly, and we'll show you how to do it. I'm kidding. But like basically, it's not easy to build a good workflow, even in the Thoughtly platform. Because there are so many things that go into it, like actions that you can take in the middle of a conversation. And things like, if a action happens, then do you put a note after it to kind of react to the result of the actions and deliver that to the callers? Those are all kind of considerations that you want to make. I would say everyone in this space are trying to make that UX, the user experience, as easy as possible for people. There's still a lot of challenges at this particular point in time. But generally, to build a good workflow, you just have to try to think of all of the edge cases and try to cover them. And you should try to make your conditions to navigate as explicit as possible so that the language model understands. One of the challenges is that everything has to be as quick as possible, which is like, the part about balancing latency. So we cannot really use reasoning models, train of thought models today, which would give us much better performance, but we just can't use them effectively. There are some techniques to perhaps combine them in a conversation setting, but that's quite tricky. But generally, I would say, don't have too much faith in language models and try to just make things as easy for them as possible. When you retrieve information from a vector database, don't include too many results. If, say, 30% of your context window are information about, are just like RAG information, that's probably not ideal. And you want to make sure that your prompts themselves don't contain confusing information. Because I've seen a lot of workflow builds where there are multiple nodes with extremely similar instructions that all kind of like loop to each other. I get confused looking at that as a human. If I get confused, I think the language model will get confused as well. Hope that answers the question.
I think we'll take one more question.
Hi, Alex. Quick question for you on the optimize your Performant Agentic Framework. With your vector, the use of vector scores in the math, is that considered symbolic AI?
I'm sorry, say that one more time.
When you optimize, when in your workflow, the agentic workflow, when it becomes more performant, and you were using vector scores, using math plus large language model, is the vector score, would that be, or the semantic index, is that more symbolic AI? Would you consider that symbolic AI? Use of symbols and so forth?
No, so it's just a simple semantic similarity, cosine similarity comparison. Yeah, for this version, yeah. You can do other things like also like doing more than cosine similarity, right? The different types of vector computation. But for this specific version that we discussed in the paper, that's what we did.